Welcome to Study Loop.
Okay, so this is problem 24.73, and it's a little bit long problem, so I solved it before starting this video, and I'm going to walk you through the solution. So in this problem, we have an interference experiment from two slits, okay, and the wavelength of this incoming light is 5 times 10 power minus 7 meters, and we're observing the interference pattern at a screen that is 5 meters away from the slits, and we have observed that the distance between two adjacent bright fringes is 2 centimeters. And the question, part A of the question, is asking about what should be the distance between the two slits. Okay, so we know the condition for bright fringes would be m lambda is equal to d sine theta, and sine theta would be just y over r, right? And so we can substitute back here, and we will have m lambda is equal to dy over r. And because this distance y here is the distance between two adjacent bright fringes, we can actually take these two fringes to be the first two, so the central maxima and the first one, and so that m will be equal to 1. And hence we can get d on one side, it will be equal to lambda times r over y. And then we can substitute, so lambda is 5 times 10 power minus 7 meters times 5 meters over 2 times 10 power minus 2 meters, and this will give us d, the distance between the two slits, which is 0.0125 millimeters. Okay, now for the second part B of that problem, it's a question about, now what if we have we have recorded the position of the fourth order minima of this wavelength, okay, and then we shined on another wavelength, okay, and we found out that actually the fifth order minima of that new wavelength is exactly at the same position of the fourth order minima of the previous wavelength. So the question is asking what should be the wavelength of the new light. So in order to solve this, I will first try to get this position, and I will call it y4. So we can actually go here, and for this, because now we are trying to solve for minimum, so the condition for the minimum is actually m plus half times lambda is equal to d sine theta. And because this is the fourth order, the first order minima will be at half, the second at 1 plus half, 2 plus half, 3 plus half. So it would be, the fourth order would be 3.5 times lambda is equal to d sine theta is y over r, and y now is y, what we labeled by y4. And then we can get y4 on one side, and it will be this, right? It will be 3.5 times lambda, which is 5 times 10 power minus 7 times r, which is 5 over d, which is this, okay? And I multiply by 10 power minus 3 so that it will be in meters. And then for the new wavelength, we will have the same condition again because it's a minimum, okay? So d sine theta is equal to m plus half times lambda nu. But now because this is the fifth order, so m will be 4, okay? So d sine theta is equal to 4.5 times lambda, and then sine theta is again y4 over r because it's at the same position, and then we can get lambda onto one side, so it will be d times y4, which we have here already, okay, over 4.5 times r. And if you just plug in all these numbers on the calculator, you'll find out actually lambda u is 4.1 times 10 power minus 7 meters. So it was a little bit a long solution, but it's actually very simple. All you have to do is actually just to keep track of the conditions for bright fringes and dark fringes. So bright fringes should be integral multiple of lambda, and for dark fringes it should be an integral plus a half multiple of lambda. And then you have just we should substitute for sine theta to be y over r, which is the position of the minima, and then you just rearrange the equations and solve it for the nu here, which is 4.1 times 10 power minus 7 meters.